Welcome to the video on oxidation and reduction, which is chapter 16 of our chemistry series. This chapter covers several key topics: defining oxidation and reduction, assigning oxidation states, balancing redox equations, and exploring their practical applications. By the end of this video, you will be able to identify oxidation and reduction, determine oxidizing and reducing agents, and predict spontaneous reactions. Could the future of transportation lie beyond the internal combustion engine? Fuel cell technology is an emerging solution for powering electric vehicles with clean energy. Fuel cell technology relies on the electron transfer between elements. In a hydrogen-oxygen fuel cell, oxygen acts as the electron acceptor, gaining electrons as it bonds with hydrogen. By separating hydrogen and oxygen, fuel cells force electrons through an external circuit, generating the electrical current necessary to power the vehicle's motor. While traditionally associated with gaining oxygen, oxidation is a broader concept encompassing various chemical reactions, from the slow process of rusting iron to the rapid combustion of natural gas. At a fundamental level, oxidation is the loss of electrons, while reduction is the gain of electrons. These two processes must occur simultaneously. In redox reactions, the species that is oxidized is known as the reducing agent, while the species that is reduced acts as the oxidizing agent. To remember these definitions, use the mnemonic oil rig. Oxidation is loss, and reduction is gain. Chemists use oxidation states as a form of electron bookkeeping to track which elements gain or lose electrons during a reaction. We assign these numbers based on a set of hierarchical rules. For instance, free elements have an oxidation state of 0, and monoatomic ions match their charge. Additional rules include ensuring the sum of states in a neutral molecule is 0, and that specific metal groups follow consistent oxidation state patterns. When assigning states to nonmetals and compounds, we follow a hierarchy where elements at the top of the list take priority. By applying these rules, you can determine which elements are oxidized and which are reduced in any given chemical equation, as shown in this example. Let's apply these concepts to everyday chemistry. Home hair bleaching kits use hydrogen peroxide, a powerful oxidizing agent, to remove color. Hydrogen peroxide oxidizes melanin, eliminating dark pigment. It also reacts with thiol groups in hair proteins, converting them to sticky sulfonic acid groups, which explains why bleached hair often tangles. For complex redox reactions in aqueous solutions, we use the half reaction method, splitting the process into separate oxidation and reduction steps to balance them systematically. First, we assign oxidation numbers to identify the components being oxidized and reduced, then divide the overall equation into two distinct half reactions. While mass is often balanced, charges usually need adjustment. We add electrons to each half reaction until the net charge on both sides is equal. Because redox reactions must be balanced in terms of electron flow, we multiply the half reactions as needed so that the number of electrons lost equals the number gained. Next, we add the two half reactions together, carefully canceling out the electrons and any other redundant species to arrive at the final, balanced equation. Finally, always verify the result. The mass and the net charge must be equal on both sides of the final balanced equation. To summarize, use this 7-step procedure: assign states, separate the reaction, balance mass, balance charge with electrons, equalize electron counts, add the reactions, and verify. When balancing in acidic solutions, you will need to account for oxygen and hydrogen by adding water molecules and hydrogen ions as necessary. For basic solutions, you take the acidic balancing steps a bit further by adding hydroxide ions to neutralize any remaining hydrogen ions. Redox chemistry is essential for life on Earth. Photosynthesis and respiration, our primary energy conversion processes, are essentially vast, intricate sequences of redox reactions. In respiration, glucose is oxidized to release energy, while photosynthesis uses solar radiation to reduce carbon, storing that energy for biological use. We can predict which metal redox reactions will occur spontaneously by using the activity series, which ranks metals by their tendency to lose electrons. Metals at the top of the series are highly reactive and easily oxidized, while those at the bottom, like gold and silver, resist oxidation, making them ideal for jewelry. Spontaneous reactions depend on the chemical properties of the reactants. As seen here, copper can oxidize magnesium, leading to the formation of solid copper, while the reverse process does not occur. We can predict if a metal will dissolve in acid using the activity series. Generally, metals above hydrogen will dissolve by forming metal ions and hydrogen gas, though nitric acid is a notable exception. For instance, zinc is located above hydrogen in the activity series, which is why it reacts and dissolves when placed in hydrochloric acid. Batteries harness redox reactions to generate electricity. By forcing the transfer of electrons through an external wire rather than directly between reactants, we create a useful electrical current. Voltaic cells, or galvanic cells, produce current through spontaneous reactions. They use half cells connected by a wire and a salt bridge, which allows ion flow to complete the circuit. Within a voltaic cell, the anode is where oxidation occurs, marked as negative, while the cathode is where reduction happens, marked as positive. Electrons flow from anode to cathode. Think of electrical current like a river. Voltage is the potential difference, similar to the force of gravity, while the current represents the actual flow of electrons through the system. The voltage produced depends on the reactant's relative tendencies for oxidation and reduction. If a reaction is not spontaneous, such as trying to oxidize copper with lithium ions, no current will be produced. A battery dies when its reactants are depleted. In rechargeable batteries, however, we can apply an external electrical current to drive the reaction in reverse, regenerating the original reactants. Visually, a dead cell shows that the active materials have been consumed, replaced by reaction products that accumulate at the electrodes. Dry cell batteries, like those in common devices, use a zinc anode and a cathode made of carbon and manganese dioxide. These typically produce about 1.5 volts, which can be scaled by connecting cells in series. Automobile batteries are lead-acid storage batteries. They consist of 6 cells connected in series, totaling 12 volts, utilizing lead and lead oxide and a sulfuric acid electrolyte. As a lead-acid battery provides power, the electrodes become coated in lead sulfate. Recharging the battery via the car's alternator reverses this process, returning the materials to their original state. Fuel cells represent an environmentally friendly alternative for transportation. Unlike traditional batteries, they generate power continuously as long as fuel is provided, emitting only water. In this diagram of a hydrogen-oxygen fuel cell, you can see how the electrochemical process efficiently converts fuel into electrical energy to power modern vehicles.